So writing the description now of the whole process is, the first point would be that why do the d subshells split due to repulsion? So due to repulsion from lone pairs on ligands, or we can say ligand lone pairs, due to repulsion from ligand lone pairs, and this only happens when a complex is formed. So when a complex ion is formed, 3D subshell splits into two energy levels. Splits into two energy levels. And we're going to show the two energy levels. So in an octahedral complex, and this is specifically for an octahedral complex. In an octahedral complex, all the ligands they approach on the axis. So in an octahedral complex, the d subshell, which is originally 3dxy, 3dxz, 3dyz, 3dx square minus y square, and you have your 3dz square. They're going to split into two separate energy levels, and you have your 3d x squared, the ones on the axis go to a higher energy level, and the ones between the axes are present at the lower energy level. Anyways, these would be the two sets of orbitals. So the next part would be that an electron from the lower energy 3D subshell or 3D orbital gains energy and moves to the higher energy 3D subshell. So it gains energy and moves to a higher energy 3D orbital. And since the next point would be that since energy is proportional to frequency, the energy gap delta E between the 3D orbitals exactly matches, or simply right matches, frequencies from the visible spectrum. And the last part would be hence a complementary color is observed. So complementary color is observed. Okay, that is going to be your 5-point or 4-point explanation. They're going to ask you to draw the splitting pattern of a 3D subshell, and you have to write. It's usually a 4-mark question, and this is all that you have to write. So why does changing ligand changes the color of the complex? So what happens now is the next part is that whenever you change any one of the ligands, like the ligands can get exchanged. So if we go and change any of the ligands, for example, the water over here could be substituted by ammonia, NH3. Now, if it's substituted by NH3, uh, the complex would change color. And the reason is that if you bring in other ligands, then the kind of repulsion that this 3D subshell would face would be different. So, for example, just hypothetically speaking, if the lone pair over here is has a very strong negative charge, then that means it would be very hard to put an electron in the green orbital. The electron over here in the green orbital over here would need a lot of energy. So this energy gap depends on the repulsion of the ligand. So if you have a different ligand, a different energy gap is created. And because of that different energy gap, a different frequency is going to be absorbed, which is why a different complementary color would be seen. So this splitting and the energy gap between the D subshell, it depends a lot on the ligand. If you change the ligand, uh, there would be different repulsions that would be faced by 3D subshell, and the splitting pattern would be different, or the energy gap between the two sets of D orbitals would be different. So I'm going to write down the description now, or the explanation for this in words now. So changing. So the thing that you're going to write down is that changing ligands, or we can say the different ligand lone pairs. So different ligand lone pairs, they exert a different amount of they exert a different amount of repulsion. And because of that, different ligand lone pairs exert a different amount of repulsion. So a different energy gap delta E is created, and since obviously E is proportional to frequency, a different frequency from the visible spectrum is absorbed. From the visible spectrum is absorbed. And that's going to be your explanation, and a different complementary color would be seen. Now it doesn't change drastically, and a different complementary. So a lot of time, the complexes are very close to in color, even if you change ligands. For example, in the case of copper, copper with 6 water molecules is blue in color, but you bring in ammonia, it becomes a darker blue. It becomes deep blue. If you bring in OH, it becomes pale blue. Okay, but if you bring in Cl minus one, then it becomes yellow. So a lot of times the changes in colors could be very gradual or slight, uh, especially when it comes to OH or water or NH3. The colors are not going to change that drastically. There's going to be some difference, but not that huge a difference. Okay, but hopefully you get the point that changing the ligands would change the color of the complexes. So the question is, why are copper 1 plus salts not colored? And for that, we need to look at the electronic configuration of copper 1 plus. Now, if you write the copper 1 plus electronic configuration, you would realize that it's argon, and it was originally copper's electronic configuration was 3d10 and 4s1. Now, because it's 1 plus, this is gone, so it's 3d10. Now, in copper 1 plus, the reason it's not colored is that copper 1 plus, the 3D subshell is completely full. So the iron has a full 3D subshell. Now, because of that, a transition cannot really happen. Like if the 3D is completely full, even if it has split into two sets of different energy levels, if all of them they have 2 electrons each, a transition, an electron cannot jump from the lower energy to the higher energy because there is no space available. So you need some sort of empty spaces so that the transition could happen. So that's the reason why if the D subshell is completely full, and that is also the case with zinc. Zinc forms iron, but its 3D subshell is also completely full, which is why, and I can add zinc to this. TK, we can add zinc 2 plus. Same reason for that. So we can write the answer electron cannot move from a lower energy D subshell to higher energy D subshell. As no empty spaces are available. Available in the D orbitals. So no transition is possible. All the D subshells would be full. So the electron cannot gain a frequency because there's no room or space available to put that electron in. Because that question might also come. What we're going to talk about now is that if you have different shapes of complexes, a splitting pattern is going to be different. The D subshell splitting pattern. So the D subshell. As we were talking about the D subshell splitting pattern is going to be different for tetrahedral complexes. Now the thing with the tetrahedral complexes, the entire splitting pattern is going to be different. Now the thing with a tetrahedral complex is, okay, if you go back and have a look at the octahedral complex. Now in an octahedral complex, all the ligands were approaching on the axis. So कौन से orbitals में electron रखना मुश्किल हो गया था? The electrons that were lying on the axis, it was difficult to keep electrons over there. Now, complexes can have all sorts of shapes. We're not going to discuss all the shapes. We're just going to discuss octahedral and tetrahedral. Now, if you go and have a look at a tetrahedral complex, which is this one over here, the one that I've opened in front of you. Usually, when you have bigger ligands, you can't fit six of them around, so only four ligands get attached to copper. Now, the thing with this is that none of the complexes are actually attacking the copper on the axis. Okay, they're all making an angle of 109.5, so none of them are lying on the axis. तो इस केस में इशू होगा कि एक्सिस के ऊपर इलेक्ट्रॉन रखना would actually be easier, would kind of be easier, because they're not, but let's say this is the axis, so the lone pair is not really on the axis. ठीक है, it's kind of at an angle from the axis, so it would be actually easier to keep electrons on the axis and more difficult to keep electrons between the axes in a tetrahedral complex. So the thing would be exactly the opposite of octahedral complex. So when the splitting happens of the D subshell. Let's go back. Okay, when the splitting happens, now in this case, the whole thing would be opposite now. That on the axis, it would actually be easier to keep electrons. So 3dx square minus y square and 3dz square would be at the lower energy D subshell, and keeping electrons between the axes would actually be kind of hard. So in a tetrahedral complex, always remember that the splitting pattern, the rest of the, I mean, why are they colored? The whole explanation would be exactly the same. There would be no difference except that you have to draw a splitting pattern in which, so you have to draw a splitting pattern in which you have the ones between the axes at the higher energy level. So 3dxy, 3dxc, and 3D YZ would be at the higher energy level, and the ones on the axis, 3D x square minus y square and 3D z square, would be at the lower energy levels. And the rest of the explanation would be exactly the same, that there's going to be an energy gap, and that energy gap would match frequencies from the visible spectrum, and electrons would jump from the lower energy to the higher energy, and when they absorb that particular frequency, it's going to be from a visible spectrum, which is why you're going to see a colored compound. So the rest of the explanation would be exactly identical.